And welcome to the last session of Summit 2013. Oh, thanks very much. Can I go now? No, it's great to see such a good crowd. I was sure I'd be here talking to empty seats for the last session. I mean, it's been a long week, right? I know I'm tired, but we'll do what we can. So, welcome to Parallel Query Execution with me. I've got a couple of compulsory slides I have to go through first, so let's get those out of the way. First time you've seen this one? Yeah. Yeah, right. You can tweet and stuff for sure, but just don't play the Star Spangled Banner or whatever your ringtone is today. Okay. Explore everything that PASS has to offer. I'm sure you have done this week. Maybe explored a little bit too much of what Charlotte has to offer. But no, there's lots of great stuff, virtual things and session recordings, and there's a PASS Summit you should try out. SQL Saturday is also good. And please do fill in your session evaluations, but only if you're going to say something nice, And I think you've still got time to win, what is it, Surface Pro or something? Yeah, it's a good prize, whatever it is. Okay, so that's the compulsory bit out of the way. My name is Paul White. A little bit about me, I'm not going to dwell on this. I blog at sqlblog.com. Adam Mechanic was kind enough to invite me there a couple of years ago. I also write articles for sqlperformance.com. And if you use the Plan Explorer tool, quick show of hands, how many people actually use Plan Explorer? Oh, that's pretty good. Yeah. There's an upload button in the modern versions of the tool. And if you upload a plan, it goes to sqlperformance.com, and I answer questions there. So if you haven't taken advantage of that yet, and you'd like a second opinion on something, it's a really cool feature, I think. Okay, I also answer questions from time to time on Stack Exchange at Database Administrators. I'm an MVP. I have a Twitter account with an underscore in it. Some other guy has got the one without the underscore. It's really, really annoying. And I also have an email address, which I encourage people to use. Okay, I really do like to get feedback and questions and things. If I get a couple of hundred in one go, there might be a delay getting back to you, but I do get round to it. Okay? All right, on to the content. According to the abstract, I'm talking about these things, and I'm going to hopefully meet all that. So the main focus of the talk really is on understanding parallel execution. I'm not going to go 500 level this time. I wore myself on that on Monday in my pre-con. But I'm hoping to give you a good intuitive understanding of how parallel execution actually works and how to read parallel execution plans properly. We're going to talk about CX packet weights, the mysterious CX packet. We're going to talk about parallel joins, and I've got some demos to show some maybe mildly surprising things to you. Okay, so let's crack on with it. The first thing I'm going to do is just very quickly review serial execution, because it's fundamental to understanding how parallel execution works. So obviously, we have a query plan, single-threaded, and it runs inside a single execution context. Now, if you don't know what an execution context is, it's basically just, if the cached plan is a template, then an execution context is derived from that with the state information and runtime parameters for a particular execution. Okay, so if you can imagine just taking a snapshot of the query plan, filling it in with things like the current value of local variables, the object IDs of any temporary tables or table variables you've created, other state information, which statements currently executing, things like that. That is an execution context. Okay? All right. And the other thing I want to emphasize, as I did on Monday at great length, is that execution plans you see in Management Studio or Plan Explorer are a summary of what happened. Okay? They're very useful for looking at a high level and saying, there could be something I need to look at there, but they are just a summary. There's a lot of detailed behavior underneath that goes on that's important to understand at least sometimes. Okay, and I'm going to talk a bit about that. So an execution plan is a demand-driven pipeline of iterators, and what that means is if you look at the execution plan on the screen, you see there's a very simple table scan returning close on 32 million rows. It's doing a count star, so that's going through a stream aggregate. But the way it actually executes is it starts at the far left. And I'm pointing towards your left now, helpfully. So it starts at the green root icon, requests a row from the stream aggregate. The stream aggregate says, right, in order to return a row to the client, I need to get a row from the index scan. The row goes back, the row goes back, and it's that sort of iterative process. Okay, so just bear that in mind. That's actually what's going on under the covers. I'm not going to break open the debugger today like I did on Monday to show you that's exactly how it works, but just bear in mind that complexity is going on underneath the covers. So, moving on to parallel execution, the reason you're here. So, we have parallel execution in SQL Server because we are looking to improve response time for largely CPU-bound queries. There is a small advantage, sometimes a decent advantage in running an I/O-bound plan in parallel because you drive the I/O system harder. But in general, you're looking to improve the response time for the client for a query that's currently CPU-bound. All right. Now, parallel query plans inevitably, or not quite inevitably, as we'll see in a demo later on, typically use more resources, so more memory, more threads, more I/O, more stuff. And to summarize, in a parallel execution plan, you have multiple threads going on, and there are multiple execution contexts. That's the key point we're going to get to. I'm going to throw quite a bit of theory at you on a few slides to begin with, and then we'll crack into some demos, and hopefully it'll all fall into place. And you can say on your evaluations whether that happened or not. Okay. So, in a nice parallel execution, you'd end up with a CPU graph. If you're monitoring the CPU, like I've got on the screen there, with a nice clean spike up to 100%, so it's massively efficient, gets the job done, and then finishes. Okay, that for me is an ideal parallel execution plan. Okay, breaking a parallel plan into bits. The first bit is there is a serial region. Okay, now every plan has a root exchange, as that little fella illustrated top right. It's always the leftmost gather streams operator in the plan. So there can be more than one of those, but always the leftmost one is the root exchange operator. It's also known internally as start parallelism. Okay? And I try to avoid that word because I fall over it all the time, so I'll probably say parallel execution instead of parallelism. So this serial region is everything to the left of that root exchange. Okay? Now in the simple count star query that I had on the screen a moment ago, there's just a single iterator running in the serial region, and it's a stream aggregate. So there can be 0 or more iterators in this region, so you can have none at all, or you can have a whole bunch of them. The important concept is that they run on the serial plan thread. So when you run a serial plan, you're already on a thread because it's processing your connection and network packets and things like that. SQL Server doesn't need to allocate a new thread to run that query. That thread is still available in parallel plans, and it runs the plan to the left of the root exchange. It is always, in DMVs and things, labeled as execution context 0. Always, this serial region. Sometimes it's called ECID in some of the old views, but in the more modern ones, it's execution context ID. Always 0. And if you look at it in an execution plan, you will see, if you click on the iterator itself or the connecting line and look at the properties window to see how many rows were processed, you'll see it labeled as thread 0. Okay, so there's this 0 thing. Okay, so if everything to the left of the root exchange is the serial region, everything to the right is the parallel region. And you can have multiple parallel branches, and I'm going to define exactly what they are in a moment. But each branch is an area of the plan that is bounded by an exchange or a leaf operator like an index scan or something like that. There's a diagram coming up to help you visualize that. Now, individual branches in the parallel region of the plan can be parallel or serial. Okay, there are certain things that force returning to serial execution for a moment before the parallelism can start back up again. So each branch in a parallel execution plan contains one or the degree of parallelism DOP execution context. So you have a branch, it's either serial or it's running, say I'm running at DOP 8, there'll be 8 execution contexts. Now if there is a serial bit in the parallel region, it does not use thread 0. It is not running in execution context 0, it is a separate thread, it just happens to be running a serial plan, its little bit of the plan is serial, and it's running inside a single execution context. Nod and wave if you're with me so far. Good nodding over here, good waving over here. Good balance, I like it. So, I have a picture at the bottom of the parallel region of our count star plan. So when I see that, in my mind, what I actually see is DOP instances of a serial version of that plan. So just take the parallel little icons, little yellow icons away, and imagine there are DOP of them. So at DOP 8, there'll be 8 of those things, all doing their own thing. Now, you'd be thinking at this stage, well, hang on a minute, how can there be 8 index scans feeding into a stream aggregate? Surely you'd get 8 times the results, right? The results would be wrong if all 8 threads did their own index scan. And the answer to that is parallel scan. And don't let the name mislead you. Parallel scan applies to full scans, table scans, index scans, whatever, but also range scans that happen as part of a seek, okay? So unless you're doing a singleton seek, which is an equality seek on a particular value in a unique index, that's a singleton seek, it goes straight to the value and then that's done. Generally speaking, a seek will have a scan component as well, so you seek down the B tree and then you scan either forward or backwards from that point until you get to the end of the range that you were interested in. Make sense? So parallel scan, this thing I'm about to describe, applies to both those scenarios. And the idea is that threads cooperate to perform the scan, so they get a little bit of it each. Now, up to and including SQL Server 2005, to the best of my knowledge, because I can't see the source code, but to the best of my knowledge, it uses a thing called the parallel page supplier. And what it means is the storage engine hands out a page of rows from the scan to the next thread that asks for it, and that's how things get distributed between threads. Works reasonably well. But in 2008, as far as I can tell, they changed it to use something called range enumerators internally. And these things, particularly on a key range, will use statistics and other things to work out a range of key values, give that to the thread, and it handles its own part of the scanning. Now, there is obviously an element of synchronization involved here, as if you've got 8 threads all cooperating to perform a scan. The thing that they synchronize on is called the access methods dataset parent latch. Okay, so if you see that weight when you're analyzing your query performance, what that is contention on the thing that is handing out ranges of rows to a parallel scan. Okay? Yes, Paul?
Yes, Paul.
Excellent. Good audience. Not bad for 4:30 on Friday afternoon. Okay. Now, important note, I've highlighted it in red, and I don't use red lightly. Only forward parallel scan is supported. Okay, so if you click on your scan or your seek iterator, go to your properties window, there's a property there that says forward or backward, and that means whether it's scanning forward in the order of the index keys or backwards. Only forward parallel scan is supported in the storage engine. I don't know why. Paul Randall has left the building, so we can't ask him, but my understanding is that they just didn't get around to it. And that was like 10 years ago, so don't hold your breath. All right, so that's parallel scan, bear that in mind. Now, in general, the whole thing about parallel plans is really quite simple. We've got these branches, and they're basically running DOP instances of serial plans, all nicely independent, reuses the existing architecture. All the complexity is hidden in these exchange iterators. They're called parallelism operators in Showplan, but the internal name is exchanges. And I like the name exchange because it's the only place that threads exchange data between them. Okay? And there's 3 types illustrated at the bottom of the screen there: gather streams, repartition, and distribute. That's the only place in the query plan that threads talk to each other to exchange data. It's actually 2 iterators in one, so it's got 2 sides to it. Remember on the first diagram, I sort of chopped it in half and said this is the serial region, and I chopped it in half and said this is the parallel? That's the reason. It's actually 2 iterators in one. The right-hand side is called the producer side, and it is stuffing rows into packets. The consumer side is reading packets and reading rows from those packets. Okay? That's how the exchange works. And if you notice on the middle of the diagram there, I've labeled the buffer packets with the word CX packet. The reason for that being that CX packet stands for class exchange packet internally. It's a real thing. It's a real C object in the code. So these packets are CX packets. And you get a CX packet wait whenever a consumer goes to the exchange and says, give me a packet of rows, and there are no packets of rows. So it has to stop, and it waits on CX packet. Make sense? Yeah. Equally, on the producer side, if it's got some rows in a packet and it wants to push it across the exchange, and the exchange is busy, or the packet queue is full, it waits on CX packet. So that's what a CX packet wait is. Last thing, a couple more things I need to say about exchanges. So all the complexity is hidden here. And one of the complexities is about row distribution. This is probably the hardest thing to get straight in your own mind about how parallel plans and execution actually works. So on the producer side, the producers have a choice about which packet to route a particular row to. Okay? And there are a number of schemes. So they route it into packets. So I'm a producer. I get a row. I can put it in that packet, or that packet. And there's a scheme. In fact, there are 5 schemes. The 3 top ones are the ones you'll see most often. There's hash, which is taking the row, evaluating a hash function on the partitioning columns, which are shown in show plan, and that tells it which packet to route it to. Round robin is very simple. You go, give you a row, give you a row, give you a row, and round in sequence. That sounds nice and simple, but it's actually one of the more problematic ones because it implicitly assumes that all threads underneath are processing at an equal rate, okay? So if one's running slowly, the whole thing can gum up and you get the performance of the slowest thread that's reading packets. Okay, so round robin sounds simple, and remember, it's putting rows into packets and the whole packet has to be full before it gets pushed across the exchange. So don't be misled into thinking that the cross-exchange stuff happens a row at a time. Yeah, that's an important point. And then we have broadcast. Broadcast is send the same row to all packets. I'll show you an example of that in a second. And there's demand and range as well. So demand is the only one that pulls a single row at a time across the exchange, having just told you that they put rows into packets, whatever. Demand is the only one that pulls a row across the exchange on demand. You don't see that one very often. Most often you'll see it with a constant scan table, and there'll be an exchange after that, and that'll be using demand partitioning. There are a couple of other instances as well, like 2005 apply model partitioning. And then there's range, which you'll mostly see in index build plans. I think and again, there's a few examples. Last thing about exchanges for the moment. There are 2 types of exchange, merging and non-merging. Now, merging has got nothing to do with joins. It just means about whether it's preserving the sort order from the threads on its input. Okay? So exchanges themselves never actually perform any sorting. They don't have any memory grant to do sorting with, but they can be set to either preserve or not bother preserving sort order on the input. Nice diagram. So I've got three threads here with rows order descending, a blue thread, a green thread, and a red thread. This exchange, if it's a merging exchange, will have the order by property, and the rows that it produces will respect that key order. Okay? It sounds great, but it introduces a dependency between threads, which is generally bad for parallel execution. Okay? Merging exchanges are more expensive than the alternative, and they can cause problems, as we will see. And obviously, the second type of exchange is a non-merging exchange. You just won't have an order by attribute, and the rows can come out of that exchange in any order that it feels like. So the first one it goes to, have you got a row? Yes, you've got a row, that'll do. And on it goes. I promised you a diagram to help you visualize branches. And this is what I do, okay? And this is not just a thinking tool. This is really how things work. So I draw a little box bounded by the exchanges and give it a different color. So this is a demo that I'm about to show you. I'm going to show you some code. And there are 3 branches in this plan bounded by the exchanges. Now, the orange and green branches are very simple. So you've got at DOP8, you've got 8 threads cooperating to do the parallel scan and stuffing rows into packets and into the exchange. Okay? The purple region is a little bit more complicated, but if you think of it as a serial plan, where instead of reading from an exchange, it's reading from, say, a scan or something else like that, it's a very familiar execution plan. It just happens to be reading from an exchange instead of from a scan, and delivering rows to an exchange instead of to a client. Okay, let's have a quick demo of that. Get rid of that. Okay, so these examples, to have enough data to show you a parallel execution plan, I'm using a larger version of AdventureWorks that add a mechanic scripted. There's a bit.ly link there to it if you want to try this out at home afterwards. So I have a simple query. It's joining 2 big versions of product and transaction history and saying, okay, how many history rows have we got per product? Very simple query. And I've got a max.1 query hint on this, just to see what the performance is with a single thread of execution and a single execution context. So I'll just run that. And it should take about 5 seconds. Yeah, not bad, 4.7. And I can run that a few times. And because it's a CPU-bound query, all the data's in memory, because I remembered to do that before I started. Oh, 4.3. Okay, so it's between 4 and 5 seconds. And if we flip over to Task Manager, we can see a little spike in the CPU on one of my cores. Okay, so it's a CPU-bound query. Now, if we remove the max.1 hint, the optimizer will choose a parallel merge join. And if the demo gods are on my side, this will take about 2 seconds or so to produce the same results. Excellent. 2.3. Now, a couple of interesting things about parallel execution plans, particularly in 2012. I'm afraid some of these things are only 2012. Earlier versions don't show everything. But if you click on the root iterator in the plan, you can see the memory grant, if I zoom it. So this query used 13 meg of, reserved 13 meg of memory for it to use. Now, there aren't any memory-consuming iterators in this plan. There's no sorts and no hashes, but there are exchanges. And these buffers, these CX packets, yeah. So in later versions of SQL Server, that is reported as part of the memory grant. If you're running 2005 or that sort of thing, you won't see any memory grant, but it's still reserved and used. Okay. The other thing of interest in 2012 is there is a thread stat thing, thread stat property, and it shows you things like the number of branches. So I'm talking about branches, the little colored zone. The number that's reported here is the number of colored branches that can possibly be executing at the same time. All right? So if you just draw the colored squares, you might have more branches than this number, but the query processor works out how many of them can be running at the same time. It'll also tell you in an actual execution plan how many threads were actually used in this execution. So this execution used 16 threads. Although, if we open the thread reservation property, we can see it reserved 24. Because we have 3 branches, I'm running at DOP 8, so 3 8s are 24. Make sense? Okay. Thank you. The only curious thing is why it only used 16. The answer to that is because although there's no guarantee in this case that one of the branches of threads will finish before the others, if we look at the plan, we can see at the top there's a clustered index scan of the big product table, which despite the name only has 25,200 rows. All right? So execution begins at the far left, as usual, gets to the exchange, attaches workers to threads, runs that purple region of the plan, goes across the exchange, starts up the index scan on the big product table, attaching workers to threads again. But that operation completes very quickly. It does not take 8 threads very long to scan 25,200 rows. So by the time the merge join opens its second input and goes across the exchange to scan the much larger transaction history table, there is a chance, depending on timing and whether the data is in memory or whether it had to go to disk or not, that the 8 threads running the orange zone scan, 25,000 rows, will have finished. And if they have finished, they can be reused. Okay? And if you run this query a few times, you can see 16 threads used, 17, 23, or 24. Anywhere between 16 and 24 for this particular query, because it's all timing related, yeah? So the engine is smart enough to reuse existing threads rather than use more from its allocation if it can. Okay, cool? Yeah. Hello. Sorry, I couldn't quite hear you. Yes, the branch information is new in 2012. Sorry? You're going to have to come to the microphone in a bit, I think. It's not in 2008, it's only in 2012 and above, that is correct. Thank you. Thank you for the help. The question was, is it in enterprise only or is it in all versions? It's in all versions. Okay. It's just a new property that's exposed in show plan output. Okay, thanks. All right, so returning to the demo. The other thing I want to mention at this point is that just asking for an actual execution plan can affect the runtime quite significantly. Because especially with that many threads running, they're all collecting statistics. Right? So this query runs in 2.5 seconds, something like that. But if I turn the actual execution plan off, please be faster. Yeah, under 2 seconds. You see? Makes a big difference. In a serial plan, the overhead's not too bad because you've only got one thread collecting data. But in a parallel plan, particularly in a big plan, it can be a significant overhead. Now, I'm just going to run that query in a loop so I can show you some things that will hopefully help settle the idea of threads, execution context, and schedulers in your mind. The point I'm going to make here is that although there are 24 threads, we're still limited to 8 schedulers in 2012 because DOP8 is the maximum system. If I had specified DOP4, we'd have 24 threads, no, 12 threads running across 4 schedulers, okay? In SQL Server 2000, you could actually use more threads than maxDOP because it would create the number of threads and just run them anywhere, and they could all run concurrently. Later versions actually enforce, if you say maxDOP4, you mean you want to be using 4 logical CPUs at the same time, and it enforces it. So I'm going to run that query in a loop, assigning the results to variables, so it doesn't produce any output, and hopefully my laptop won't melt while I do this. It is a risk. Okay, so that's running. And we have a few helpful DMVs, like SysDMOS tasks, workers, and threads, which we can join together in a natural way. Set it to session ID 57, which is where I'm running my query. And you can see we have at the moment, there's 13 rows there, 15, 17. So we have 2 branches of 8 threads, 16, plus the 1 serial zone thread provided by the connection. So we have 17 in total, and at any one time, 8 of them will be running, hopefully, or waiting for something from disk or some other wait type, and the other 8 will be suspended. And you can see they're spread across my 8 schedulers here. And they have an execution context ID, and the serial zone execution context is always 0, and it is always the parent task. And you can see here the wait types. So if it's waiting to read from an exchange, it's a CX packet wait. Now, if I run the same query, but order it by scheduler ID, it should be clearer that there are generally 2 threads running on each scheduler. One will be suspended, one will be running. So that's how it limits the number of concurrent threads that are running. All clear? Now, these DMVs aren't transactionally consistent, so you can get strange-looking results, but generally, if you run it again, it'll all make sense. And the last thing I want to show you is the very useful SysDMOS waiting tasks. So I show them what's waiting. Like I say, here in my execution context, this is how long they've been waiting. They're waiting on CX packet, but the resource description is really interesting and useful. Excellent. For the benefit of the viewers at home, that was somebody blowing their nose. Or possibly an entertaining ringtone. Okay, so the description here, right at the end, there's a wait type of wait pipe get row. So there's a CX packet, there are CX pipes and CX transports and all sorts of CX stuff going on under the scenes. But wait pipe get row means a thread is waiting to get a row. You're right, Maria. Okay. Something is waiting on the consumer side of an exchange to read a row. Okay? If something was waiting because the exchange was full of packets, the wait type would be wait pipe new row. And the interesting thing is right on the right-hand side here, it says node ID. And this is the node ID number that you can see in execution plans. So we can see a whole bunch of stuff waiting at node ID 6, and one execution context 0 is waiting at node ID 1. So let me stop that query before things burst into flames over here. Show you the estimated plan. So most of the stuff was waiting at node ID 6. And if I hover over this lower exchange, where most of the work's going on, to be fair, you can see my zoom it skills are fantastic. You can see this is node ID 6. So by correlating that DMV with your execution plan, you can see what's waiting where. Yeah, really useful. If you want to if you need to do some detailed analysis. And node ID 1 is the serial branch coordinated thread waiting there at node 1. All good? Yes. Excellent. I'm actually doing okay for time. I might actually get through all my slides and demos today, which would be something of a first. Wouldn't it, pre-con people? Yeah. Okay. back to the slides. Now, a quick word on parallel joins, because there are a couple of interesting things here. So parallel merge join. You'll always see two exchanges on the inputs to a merge join, parallel merge join. And it'll always use hash partitioning. The point of hash partitioning here is because there are 8 instances at DOP8 of this merge join, so we have to guarantee that all rows that are going to join end up at the same merge join. Yeah? It's no good product ID for going to one and then product ID on the lower branch going to a different exchange. We get wrong results. So hash partitioning is the way they do that. It's hash partitioned on the join keys for the merge join. So what that means is that all the rows for the same join key will end up at the same instance of the merge join. Now, because it's a merge join, it requires sorted input, so these exchanges must be merging exchanges. They will have the order by property on them. Merge join does not scale particularly well, but as DOP increases. Merge join, in general, is not favored by the query optimizer because it has particular issues to it. I kind of alluded earlier to the fact that preserving sort order and that sort of thing is bad for parallelism because it introduces dependencies between threads. Merge join is a classic case of that because it is requiring sorted input, so it has to have things in a particular sequence and things have to coordinate with each other. And there is an increased risk of parallel deadlocks, which I hope to show you in glorious detail in my last demo of the day. Parallel hash join. Yes, question? So the question was long and complicated. The answer is, you remember the nicely colored diagram I showed you of it preserving order? It's just that those 2 exchanges below the merge join have to be doing that extra work because merge join requires sorted input. Okay? Is that good enough? Sweet. Okay. So parallel hash join, you have 2 main choices. You have, if the build input is small, so the input that is building the hash table for the hash join, if that input is small enough, and there's a hard-coded number there somewhere around the 100 mark, something like that, then you can get broadcast partitioning. And what that means is you just get one exchange on the build input to the hash join, and that uses broadcast partitioning to send the rows to all threads, okay? So on the probe side of the hash join, you won't see an exchange because it doesn't need to distribute the rows because they've all got a full hash table. So they can just probe for matches straightforward. It does use a lot more memory though, broadcasting to all threads, hence the low number of rows requirement. The other alternative, the one you'll see most often to be fair, is similar to the merge idea, where you have 2 exchanges that are using hash partitioning to make sure rows that are going to join end up at the same instance of the hash join. All right? So you should have this idea in your memory now. You're looking at it and you're seeing a parallel hash join, but at DOP8 you're seeing 8 of them, and they're operating on disjoint sets as inputs and cooperating to produce the output. Obviously, the normal problems with hash join. I mean, it does scale very well with parallel execution, but it can spill if the memory reserved for the hash table winds up being too small. Another demo. Because there is something special about hash and merge join that you'll only see. And although I said on my first slide that in general parallel plans use more resources than serial plans, there is an exception. An interesting exception, I hope. Okay, demo 2. Ooh, no, that's come up in the wrong order. Okay, demo 2. So I have 2 tables. I'm going to create 2 tables here, just with a single column. The first table is going to have 5,000 random positive integers, and the second one is going to have 5 million random positive integers. Now, because it's random, there is an element of risk that this demo will not work. So if you'd like to cross your fingers in the front row. So we have 5,000 rows in one table and 5 million in the other. I'm going to create some statistics so we don't get a delay while that happens automatically. And the query is a very simple one. It just joins the 2 tables together and says how many matches are there. So given these random numbers, how many matches did there happen to be? And if we run it at .1 on a serial plan, the query should, it's 7 matches, that's about typical. And it runs for around about a second. Okay, this one's gone a bit quicker just to make me look silly. 850, 900, something like that. Yeah, all right, settled down to about 850. And everything's in memory, so there's nothing coming off the disk here. This is as fast as it's going to go. Now, if we run exactly the same query, just at DOP2, so the minimum that can produce a parallel plan, get the same number of results back. But the CPU time is lower. Okay, so it's used less CPU, it's used fewer resources, and the elapsed time is 311. Okay, now on a typical run, you'll get about half the CPU and 4 times faster, but because I'm sat in front of you, it's about, it's a little bit less than that. And the reason for that improvement is that in this execution plan, you'll see a bitmap iterator, and you can only get this in parallel plans. All right? You can get it with parallel hash join all the time, and you can also see it in parallel merge join plans if there is a blocking iterator like a sort on the input. The idea is that as rows flow through, it uses a Bloom filter to set bits indicating which product IDs, in this case, it has seen. And when the hash table is built, it passes that bitmap across to the probe side of the join and says, before the rows get to the join, apply this Bloom filter to filter out any rows that can't possibly match. So it's an early semi-join reduction, is what it's called. And if you click on the bitmap, you'll see it is defined and given a name of bitmap 1008. And some iterator on the inner side of the hash join will reference that bitmap. And in this case, it's on the table scan. And you can see it says probe bitmap 1008, so check the bitmap. And it's also got the in-row attribute in this case, which means it's used the most efficient mechanism possible. It's pushed the bitmap deep into the storage engine. So as the storage engine is finding rows, it's testing them against the bitmap before they even surface into the query processor. Okay? The upshot of all this is that instead of the estimated 5 million rows we expected to get from this table scan, applying the bitmap filter early, oh my goodness. Shall I run an actual execution plan? Yes. So, as I was saying, instead of the 5 million rows we were expecting, in this case, we've only got 2,596. So everything has to do much less work and things run more efficiently and quicker. So that is a parallel plan that runs faster using fewer resources. Now, because Adam Mechanic is not at Summit this year, I have to also cover parallel nested loops join. Last year, I could just say go to his session. But, this is a technique he showed me getting on for 3 years ago now, and it surprised me at the time, but I've used it non-stop ever since. So I'm going to spend a couple of slides talking about this. So, the most useful type of parallel nested loops join is the apply pattern. So it's a correlated join. And you can tell it's a correlated join because on the nested loops iterator, there'll be an outer reference, in this case, product ID. So, when we're counting the history rows, it says for each product ID, count the rows. For each product ID, count the rows. Correlated join. The special thing about apply, the parallel nested loops join, is that the inner side runs serially per thread. Okay? If you think about 8 threads cooperating to perform a big sort, for example, which we'll come on to in a second, they get 1/8 of the set each. Yeah? So they're working on a big set. With an iterative nested loops join, it's a divide and conquer idea. So for each product ID, it does a little bit of work, counts the history rows, gets a new product ID, counts a bit of work, and 8 of those threads are doing that same iterative thing at the same time. So you get all the benefits of parallel execution, but the individual bits of work are smaller. All right? It's a subtle difference to get your head around, but it's a very important one. Because the benefits of this, the serial running on the inner side of the join, is we can get fewer exchanges, as you'll see in a minute. We can eliminate some exchanges from the plan. We can avoid serial branches completely. So normally in a plan, you'll see if you use a top or something, you'll see an end to parallelism, a little serial branch as it works out the top across all the data, and then it will start parallelism again. That's very inefficient. But because the inner side of a nested loops join per correlated parameter is running serially, from a single thread's point of view, it doesn't need to stop and restart parallelism because there is none going on. Crucially, also, you get smaller memory grants, because if we're just counting the rows for a particular product ID, we're working on quite a small set. So we only need a small memory grant for each iteration. And we can reuse that memory grant instead of having one big memory grant to perform 1/8 of a sort, for example. The disadvantages of parallel nested loops join are that the read ahead on the inner side of the join is generally not as aggressive, not as big. which can have big performance implications. You can get skew across threads quite easily. And the query optimizer is heavily biased against using this pattern. You can have to fight to get this to work well, but when you do, it works extremely well. So what I mean the query optimizer is biased against this pattern? Well, you have to fight the cost model a little bit. For reasons that I don't fully understand, and I know the optimizer reasonably well. In general, the reason it picks a parallel plan is because it reduces the estimated CPU cost by the expected DOP. Okay? It makes the iterators cheaper, right? But that doesn't apply to the inner side of a nested loops join, and I don't know why. I don't know why. So it tends to overcost a parallel nested loops join plan, so it tends not to pick it. And there are a number of assumptions as well, like the cold cache assumption, the fact that sequential I/O is a lot better than random I/O, and all that sort of thing. All these things combine to mean that parallel nested loops join is often a difficult plan to get. So what can you do? Well, you can ensure the optimizer has accurate information. That's always a good thing to do. You can express the query using different syntax. That sometimes works as well. You can get a parallel nested loops join plan. You can use tricks in your query. You can write your query in a particular way. You can mod this. Did anybody go to Adam Mechanic's manhandling parallelism talk last year? Maria, you did, a few people here? Yeah, so you've seen some of the tricks he uses with top and optimize for and that sort of thing. You can do that. That's fine, as long as you accept the consequences of what you're doing. Yeah. You can also use an undocumented but very useful trace flag, 8649. We don't have a min-dop hint. We have a max-dop hint. We don't have a min-dop hint. I would dearly love a min-dop hint. Every time I see Connor Cunningham, I say, can we have a min-dop hint? And he says no. So there is no supported hint to say, I want a parallel plan, please. Okay, and the closest we can get is this undocumented flag 8649, which is tremendously useful, and will give you a parallel plan if it's possible. So it's useful for just checking if you can get a parallel plan, for example. It's a risk to use it in production, obviously, because it's undocumented and unsupported, but you can use it to produce plans that you can then use as a plan guide. If it gives you the plan you want, you can use it as a plan guide. Personally, I do use 8649 in production, but I know what I'm doing and I accept the risks. Okay. So, I talked about one of the advantages of nested loops join in being in eliminating an exchange. So let's see a quick demo of that. And it better be a quick demo as well, because I'm down to 33 minutes. I'm not doing as well as I was. Okay, so back to Big AdventureWorks. And if you remember, the original merge join parallel query ran in about 2 seconds or so, used 13 megabytes of memory for its exchanges, reserved 24 threads, and used somewhere between 16 and 24. You remember all that? Do you remember all that? Yes, Paul. Cool. So my first attempt to write this as a nested loops join was to use cross-apply, and to say, okay, for each product from the big product table, cross-apply, give me the count star for that particular product. So I write that query, and the optimizer says, nah. The optimizer says, nah. And it transforms it to exactly the same plan as if I'd written it, using an explicit join, which is annoying. As I say, this whole costing thing can mean that the optimizer sometimes thinks, I know better than you. And a lot of the time it will do. But I'm not actually going to run that query because it's just exactly the same as the first one we saw. My second attempt then, I thought, well, perhaps I can get around this transformation from the apply to the join by putting a non-relational operator in the query. So I put a top one in. Obviously, the count star is only ever going to produce top one. If the optimizer had this rule built into it, it could throw my top one away as redundant and go back to doing the join. It's not currently smart enough to do that, but it produces a serial plan because it costs up a parallel alternative, doesn't reduce the inner side costs by the expected DOP, and it comes out looking more expensive to the optimizer. It never picks plans that it thinks are more expensive than another one it's found. But it's annoying, because that's a serial plan, and I know I've got lots of rows. I've got 32 million rows in one of these tables. So I gave up at this point and used my trace flag. So, well, it's not my trace flag. I didn't write it, but, I came across it somewhere. 8649. Okay, and I'm using it with query trace on in this case. And that gives me the parallel plan that I was looking for. Success, right? Yeah. And if I run that query, it runs in just under 2 seconds, which is, pretty good. And if I remember to put actual execution plan on, I can show you some stuff. I mentioned the problem of thread distribution sometimes. And if we click on this link here and look at the actual number of rows in the properties window, oh, actually, that's not too bad. Yeah, that's distributed across it quite nicely. Oh, well, all right. Thanks for that, demo gods. So anyway, we've got the cost down from just over 2 seconds to 15.91, which is a success. And we've done that because if you remember, the original merge join plan had 2 repartition exchanges that were merging exchanges before the join, whereas in the parallel apply plan, we've only got the one final exchange we must have, the root exchange. There are no other exchanges here. They don't need to be, all right? Because think your thread 3, for example. Thread 1 and 2 we don't like. Thread 3, you pick up a row from the clustered index scan of big product, so you're dealing with product ID number 1. You go to the nested loops join, you're dealing with product ID 1, the inner side is correlated on that. You do an index seek to product ID 1, you get a number of rows, you count them, you do this meaningless top that we just got there to get the right shape, and then you go back and get the next product ID. So you see how this iterative thing works. You've got 8 threads picking up the next product ID that they need and all cooperating nicely without the need for any additional exchanges. Is that making sense to everyone? You're so much better than the audience I had earlier in the week. Yeah. Sucking up for the evals. Yeah. Okay, and I sort of alluded to this a minute ago, but it's worth mentioning because it's so important. Many problems can be expressed using apply. So you have lots of problems where you're writing a query to reduce something per customer, per supplier, per account. Itzik Ben-Ghana's written about this, the flexibility of this technique. It's in at least one of his books. It's on SQLmag.com. Adam has written about it a number of times. It's a pattern that applies to real-world queries quite nicely. And as I said before, you can use smaller memory grants that can be reused. So we had our big merge join query. We might need 300 meg of memory, but with the nested loop join plan, we might only need 8, yeah, because we're reusing it on each iteration. And because our query needs less memory, we get all the benefits of that. So we don't have to wait for our memory grant if the system is under memory pressure. There's less impact on the buffer pool, because whenever your query gets a big memory grant, it has to come from somewhere, right? And it was probably being used to cache valuable index or data pages before. And you get improved concurrency, because more people can run more queries at the same time, from a memory grant point of view anyway. And it turns out, this is Adam's point from last year, and this is the thing I learned from him. The computational complexity of a sort is n log n, apparently. So if you do the maths, one big sort at n log n is actually more costly than doing a number of smaller sorts that come to the same set size. That surprised me, but if you do the numbers, it's actually true. So it's actually more efficient, apart from anything else. I'm going to come back to the parallel sort demo at the end, because I'm running a little bit short of time. So to summarize, good things you want to encourage in your parallel execution plans. We like an even distribution of work across threads if we can. It's not a guarantee of success, but certain things like parallel sort, for example, the memory that is granted to it is split into bits. So if you have 8 threads and you get a memory grant of 8 meg, each one will get 1. So if more rows go to one particular thread than another, they can't borrow memory between them, yeah? And it'll spill to disk. You don't want any threads to get left behind. So when your query is running, you want them all to finish at the same time, roughly. So get the same amount of work, get the same amount of CPU, all finished together. That would be ideal. You get a nice clean spike in your CPU graph. We want short CX packet weights in general. I mean, in general, I don't worry about CX packet weights very much, yeah? Because if you think about all these threads, reading and writing to exchanges and all the rest of it, if one's waiting, it might just be that the other threads have got lots of work to do. You're still keeping your CPUs busy. There's no way to make it go any faster. They might be waiting on a read from disk, in which case you need a faster disk system, but you'll have another wait shown there to tell you about that. So in general, CX packet weights I don't really worry about, unless I see extreme weights, and that means that maybe I've got a skew problem. So one thread is completing long after the others. But in general, I don't worry about them too much. Other good things, we like unordered processing. So when these branches can run independently of each other without any dependencies, it's good for the pipeline as a whole. And we want our query to be CPU bound, ultimately. That doesn't mean that each query you write uses massive parallelism and brings the system to its knees. Yeah? You might give it a bunch of CPUs to use, whatever, but ideally the query would be CPU bound. Otherwise, why are we using parallel execution in the first place? We'd do something else. Bad things. There are lots of bad things to watch out for with parallel execution. There are certain things that can prevent you getting a parallel plan at all, regardless of whether you use magic trace flags or anything else. Whether you sacrifice a goat to the god of parallel execution, it won't help. T-SQL scalar functions, apart from being the single most evil thing in the world ever, because of the way they're implemented, completely disable parallel execution for the entire query, if you reference one. Modifying the contents of a table variable. I mean, there are a bunch of things, but you can read it for yourself. But interestingly as well, accessing a system table. So I sometimes write a test query to get a parallel plan, and I access systables or something, and oh yeah, that's not going to work. Yeah. But there are less sneaky things that will force a serial branch in your plan, unless you're doing something clever with the inner side of a nested loops join. So a global top, for example, if you say top 100, obviously all those rows have to come together onto a single thread before it can say there's 100. So you get a little serial branch in your plan. And stopping parallel execution to do that on a single thread and then restarting it again is wasteful and inefficient. We don't like it. Window functions pre-2012 would have to stop parallelism while they applied the sequence project and the segment. That's a big improvement in 2012. And generally speaking, later versions do allow more parallel things than earlier ones. So keep as current as your budget will allow, I suppose, is the message there. Multi-statement functions, almost as evil as the scalar ones, but they only force a serial branch, not a whole serial plan. And as I mentioned right at the start, because parallel backward scan is not implemented in the storage engine, that will force a serial branch as well. So if you look at a query plan, it's nicely parallel otherwise, but you've got this single seek or scan that is serial, and followed by an exchange, a distribute streams exchange. I almost guarantee you the reason that is serial is because it is performing a backward ordered scan. Yeah? So look at providing an index in the other order or some other change to mean you can get the whole thing running nicely parallel from the word go. And excessive parallel execution is obviously a bad thing as well. So parallel plans get a bad name because they say, oh, I've got max top 0 on my system, and I turned it on, and my SharePoint site. No, I'm not going there. I'm not going there. But no, you don't want too much parallel execution either, right? So proper, efficient, nicely done parallelism is super fantastic, but obviously, so you want to do the basic things, right? So you want to set your cost threshold, to a sensible level so that the sort of queries you want to go parallel tend to, and the smaller ones tend not to. I mean, the default is 5, which is way too low, right? So you probably have it set, somewhere 35, 50, something like that. That's a number I find works reasonably well. You want to set your default DOP appropriately as well. So max DOP 0, not always a great choice, not always a bad choice. I like 8. Now, it's impossible to make a recommendation, but I do like 8 personally. But some people say the number of physical processors, sorry? 8 is a pretty number. Yeah, it's a power of 2. It's got all sorts of things going for it. And very lucky in China, I understand. Back on track. So some people say, start off with a sensible number like the number of physical processing units you've got per NUMA node. That's all sensible. Sounds rooted in theory. I'll go with that. But of course, you want to test it and see how it goes. My parallel deadlock demo. This is the one I want to show you because it's kind of cool. And it took a bit of effort to get it to work. When I was talking earlier about the dangers of merging exchanges and retaining sort order and things, so certain query plan iterators like stream aggregate and merge join and a few others, they sort of naturally require or preserve order as they go through them. And order preservation really is the enemy of efficient parallel execution in a lot of places because of the dependencies. Now, I really wanted to show you, I wanted to show this for many years, but the problem is I only really came across it in very big, complex plans that wouldn't really look very meaningful on the screen, and you just go, oh yeah, that's neat. So I wanted to get a nice, concise, albeit slightly artificial demo to show you. And here it is. Deadlock. So the important business task of the day is to use our numbers table, which is just a table with a single column with all the numbers from 1 to, I think I've got 10 million or something. We're going to use our numbers table to compute the highest even number that exists that is less than 30,000. You probably run this query all the time. And the way I've chosen to express this query is like this. Okay? Now, if you work through the logic, you'll see it will, in fact, eventually find the highest even number less than 30,000. And I've done a couple of tricks here. So I've said we'll find even numbers by saying mod 2 is 0. And I've got a strange-looking convert to varchar max in there. And I've also used the magic 8649 trace flag as well. Now, if we run this query at DOP3, we get our result. The highest even number less than 30,000 is indeed 29,998. And it took 31 milliseconds to run that query. So I write good code, right? Yeah. Yes, Paul. Okay, max dot 5. 0 milliseconds. Goodness me. 31. It's all good. Max dot 7 is as high as I can go on this laptop. 16. So it's all working well, right? What about max dot 2? Let's run that. Oh, still running. Still going. Okay, that's enough now. There we go. 9.5 seconds, everyone. What on earth happened there? So, again, this is only 2012. You see this little warning thing here on the exchange? The little warning icon? Yep. It says, very good. It says, operator used tempdb to spill data during execution with spill level 0. So it's a generic message. There is no spill level like there is with sorts and hashes for an exchange. Basically what happened here is things got gummed up, and it got into a state where it couldn't make any progress. It's a deadlock. And these deadlocks are resolved by the normal deadlock monitor, the same thing that resolves the deadlocks that you don't have in your highly tuned production systems. But it only wakes up once every 5 seconds by default, right? So the query has to get stuck for 5 seconds, unless you've had a recent deadlock, before it'll spot it. And the way it resolves the deadlock is by asking the exchange to spill its CX packets to tempdb disk, all right? And as we increase the DOP, at even DOP, it gets worse. So I've got like 10 minutes, so we'll let this run. Oh, well, it didn't get worse in this case. But again, you'll see this little warning symbol. Unfortunately, in earlier versions of SQL Server, you can get these parallel deadlocks, but you don't get the warning icon. You have to be running profiler, the exchange spill event something warning thing, or something extended eventsy. But again, another reason that 2012 is so much nicer to work with execution plans. Now, another interesting feature here is you notice this clustered index seek is serial. It hasn't got a parallel icon on it. This is all part of why the demo works. But just to prove the point that I was making earlier, you see this scan, this carefully crafted scan, is backward, yeah? And therefore cannot be parallel. All right. So what's going on, Mr. White? What is going on with this query plan? So, and why does it only happen at even DOP? I should have a prize or something, like a Ferrari, yeah, and give it out to anyone that gets this. And this isn't meant to be a realistic example, but this does happen in real production queries. If you have merge joins and stream aggregates and all these other order-preserving things, parallel seeks, if you get them and you're just a bit unlucky with data distribution or whatever, you will get a parallel deadlock. You won't get a warning or an error message or anything else. It will just run slowly, yeah? And unless you happen to be tracing the right event or whatever, you won't know why. But anyway, in this case, so we have our serial backward scan. Hi there. It's taking my photo again. So we have a serial backward scan, all right? Then we have an exchange, because I've said I want a parallel plan ready with 8649. So we have a distribute stream exchange to distribute those rows coming from the scan part of the seek across threads. And that exchange is using round-robin partitioning, all right? So even DOP goes to one thread, goes to the other thread, yeah? I drew it out. So if we had 100, 99, 98, 97, 96 coming back from the seek, the distribute exchange, because it's using round robin, ends up putting all the even numbers on one thread and all the odd numbers on the other. The filter is throwing away all the odd numbers, so you end up with just a stream of even numbers, right? The last exchange is also a merging exchange. But in order for that exchange to produce its first row, it must have received one from all of its thread inputs, right? Because it's a merging exchange, it has to return the one that sorts highest. And it never gets a row on the other thread because they all get messed out. But at odd dop, the distribute streams, if you think about it, puts the numbers, yeah, so it does get a row and things don't jam up. All right? Now, it is a very artificial example, but it does happen. It does happen. So I'm going to take some questions at this point, and if we don't have any, then I'll go back to that demo I was going to go into a bit more detail on. Does anybody have any burning questions they want to get up and go to the microphone and embarrass themselves with? Yes, you do. Go on. I got up here. Round of applause, I think. I feel this is going to be a great question. Yep.
This one, I guess it's pretty simple, but the thing you were talking about with the max stop, with it being even, is that specific to that example, or is that more of a generalization?
Oh, right. So if you didn't hear that on the recording, the example I just showed, is it the fact that it's even dop, does that apply to bad things in general with deadlocks? And the answer is no. Okay? It just so happens to be a nice, simple way that I could write the query to get the demo to make it fit on one slide. Okay? Parallel deadlocks can happen just through an unfortunate data distribution wherever you've got preserved order. I think Craig Friedman wrote about it in the 2005 internals book, and there's a number of, you have to have like 3 different order preserving things, and if the distribution is unfortunate, you'll get a deadlock. Okay. Any other burning questions? Yes. You don't get a round of applause because you weren't first.
You showed that bitmap thing, right? Parallel. What happens in the serial when it is a serial plan? I didn't get that. So.
Oh, you want to see the serial plan for the?
For the bitmap. So if it is a parallel, it goes to the storage engine and takes that, right? So what happens in the serial level, serial plan?
Okay. I think the question is, why don't you see bitmaps in serial plans?
Yeah.
Yeah. In fact, there is a bitmap inside the hash join operator in a serial plan, right? But it's only used if a spill occurs. I've got a blog post on it, actually. If you go to sqlblog.com and read my blog post on bitmap magic, I explain it in glorious detail.
Sure.
Okay?
Thank you.
I'm not sure I could do it right now because it's Friday. We've had a long week. So if you don't mind, I'm going to show you one of those. Oh, okay. Yeah, question? Yep. All the way over here, bro. My goodness, your accent is harder than mine. Could you say that again? I'm sorry, I'm really bad with...
My query is running right now.
Your query is running right now, yep.
Right now. And I would like to know if there is a way to determine if any of these partition threads has a skew distribution. Is there a way?
Right, yes, good question. Is there any way to know for a currently executing query whether you have a thread skew problem, so whether they're all going onto one thread and the other? Currently, no. But there are encouraging signs that for SQL Server 2014, there is going to be some really quite cool DMVs, which I'm hoping make it into RTM. I mean, it's on books online. You can see it. You can see it on the web there. It seems to be showing us what's happening at each iterator during execution. Yeah, and I really hope that makes it to the final product, because that's going to be so cool. All right. So I've got 10 minutes. I'm going to show you one of the demos I didn't have time for, or I thought I didn't have time for. Can you believe I actually managed to time a session correctly and raced ahead? You can. Thank you for that, sir. All right. So this is a demo about the efficiency of breaking up sorts. So I have a typical query, a typical parallel query here. And I've completely ripped this off from Adam Mechanic's session last year. And the idea is to join the product and transaction history tables, and then to compute 2 different ranking orders on the result. The details of the query don't matter too much. The fact is there are 2 different ranks in incompatible orders going on. And if we ask SQL Server, the optimizer, to come up with a plan for this query, we end up with a few iterators needlessly in the serial zone of the parallel plan, a sequence project and a couple of segments for one of the ranks. Then we have a sort to get it in the right order for that operation. Then we have a parallel sequence project and 2 segments for the other rank, another sort to get it in the right order, excuse me, a parallel hash join, and reading from the base tables. And again, the exchanges will be using hash partitioning. Okay. Now this query, could you please silence yourself, man? No, good on you, I don't mind, it's quite funny. So we run this query for product IDs between 1001 and 3001. So it's a little subset. It doesn't return any results because I'm assigning them to variables. And this should take about 10 seconds. Yeah. There it is. Now, if I'd remembered to put the actual execution plan on, what you would see is that the query reserved 301 megabytes of memory for its exclusive use during its execution. Okay? There we go. Which we can see by clicking on the root iterator and looking at the memory grant info. So on earlier versions, you just see the memory grant. On 2012, you see a bit more of a breakdown in terms of what it asked, what it would have liked, what it got, and things like that. So 300 megabytes, that's in kilobyte units, right? That's quite a lot of memory grant, right? Yeah, and it used almost all of it, yeah, that's right. But our sort still spilled. There you go. Warnings, operator used tempdb to spill data during execution with spill level 1. We don't like spills. Spills are bad. But the interesting thing as well is we have 2 sorts, and they're sorting the same data set, right? For the ranks, first one way and then the other. That sort spills, but this sort does not. Let me do something flash with zoom it. There we go. This one doesn't spill. Anyone know why? I'll tell you why. And almost nobody knows this. When you click on something that consumes memory, like a sort, there's a property called memory fractions, which means given the order in which things execute in the query plan, what fraction of the grant for this query was available for this iterator to use? And sort has 2 phases, yeah? So it reads rows into its input buffers, performs the sort, and then starts producing rows. So it has an input and an output phase. And the memory fraction says, right, when it's reading rows into the sort, it has 0.9873332 of the memory grant. So basically all of it. That's why it didn't spill. It had almost all the 300 memory grant to work with. But on the output, it only had half, right? And the reason being, the output phase of that sort is running at the same time as the input phase of this sort. You're looking blank at me like, really? You're telling me this on a Friday afternoon? Yeah. But the memory fractions on this sort iterator say on the input you only have half. Yeah? So you have 150 meg to work with for your exclusive use. Right? Because it can reuse memory that's been finished with, right? But because they can be running at the same time, it only gets 0.5. And therefore, it has to spill to disk. You are now an advanced query tuning person if you know that. So that's bad. And one of the things people do is they say, oh my goodness, what we need to do here is to give this query more memory grant. And one of the tricks I see used occasionally is they'll artificially inflate the size of one of the columns, okay? Because memory grant is reserved on the basis of the expected set size. It's there's a complicated algorithm, but essentially that's one of the main inputs to it. So product number, which is nvarchar 56, if I convert that to twice its size, 112, has anyone seen this trick or used it before? I've seen it blogged about before, and I do see it from time to time on forums. So I express my query slightly differently, same range of product IDs. It now runs in 3 seconds. and the sorts do not spill. All right? Because we've artificially inflated the memory grant. And we requested and got 425 megabytes of memory for our one query. Right? Which is a success, but the query is now ugly. The query is now ugly and hacky, and we're using nearly half a gig of memory. Yeah? My laptop has 8 gig of memory. Yeah? We will not be running many concurrent queries. Now, I'm not going to run this because it just takes forever, but if I now expand the product ID range, if I double it from 3,000 to 6,000, because of the limited amount of memory in my machine, it'll ask for something over a gig, but it won't get it. Yeah? The default limits for the resource governor, I always forget what they are, but it's something like 25% of the default pool or something like that. Anyway, it asks for a gig, doesn't get it, the sort spills and performance is terrible. But if we apply our apply technique, so correlated nested loops join, and say, what we're going to do here is do the sort per product ID. Yeah? Because the rank was partitioned by product ID and then ordered by something else. So we can take that partitioning out, do a nested loops join. Yep, you're all nodding at the front. Excellent. Excellent. It took me ages to work out what Adam was talking about when he first showed me this, but I get it now, and it's a very powerful technique. So let's try that. Cross-apply with rank. And this is on the bigger range now. This is twice the range. There you go, about 5 seconds. All right? Nice parallel plan. Or so it seems. If I click on that, look at the actual number of rows. There's only actually 2 threads doing any work. Parallel scan distribution is not perfect, the algorithm. Remember I talked about parallel scan, giving things between threads? It's not a perfect algorithm. And so you have to be very careful to check those things. Tools like Plan Explorer make that much easier to see, because I can open this plan in Plan Explorer and I can see all the iterators at the same time with their thread distribution rather than clicking on each one and expanding that node. Yeah? So if there's anybody out there that hasn't at least tried Plan Explorer, you should get it just for that. Yeah? It makes parallel things much easier. So what can we do about this thread distribution problem? Well, there are a number of things you can do. Adam would write a nested subquery and put top and optimize for and something else. I'm going to put the driving product IDs into a temporary table. So I'm going to take the records that I want, put them into a temporary table. And to be fair, I'm going to measure the timing, including the time to create the temporary table, populate it, and then drop it at the end. So I'm going to put my product IDs between 1001 and 6001 into a temporary table. I'm then going to create a primary key on that table and run a nice simple cross-apply query from my driver table to do the 2 ranks one at a time, and then drop it and then show you the elapsed time. Yeah? You're a smart person. The question is the cluster key required to get the stats for distribution? Yes, it is. So in this particular case, I wanted to create an index and for it to gather full scan stats, because stats are one of the things that drive the range enumerators. So yes, that's how I'm giving it better information to work with. Okay? So the elapsed time there is 3853. If I go down to my query plan and look at the distribution across threads, you can see now the distribution is not perfect, but it's perfectly good enough. All right? Perfectly good enough. If I turn my execution plan off and run it again, remember this is still the very large set, the double-sized set. 3, 3, 2, 4, 5, yeah? Which is, even when it didn't spill the original plan that ran in 10 seconds, used a huge amount of memory grant. How much memory did this plan use? Let's see. 5.5 meg. Awesome, eh? Okay, ladies and gentlemen, I have 1 minute remaining, which is just enough time for you to stand and clap and throw flowers. Thank you. Thank you for coming. I enjoyed that. That was fun. There's my contact details if you need them. If you want to send me an email or whatever. Thanks, guys.